Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In the previous video in this series, I introduced you to the basic goals of impedance matching. I also introduced you to the basic elements of the full color Smith chart in preparation for this video. If you missed that one, I've put a link up in the corner for you. In this video, I will be walking through how to design an L-type A impedance matching network using the full color Smith chart. This matching network only requires two components, and they are the simplest to design. I will accomplish this by way of an example. Now, I've placed a link to the full color Smith chart that I used in this video down in the description for you. There is also a link to a zip file in the description which contains other associated goodies like, well, the formula sheet, the list of basic rules, and the OCTAVE file. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, I'm going to begin by setting down some basic ground rules that are essential to make this happen. What you will find when you seek to understand this whole process are people who will quickly show you examples while they operate under a set of unspoken ground rules. You then attempt to do the same thing with your own design, and well, it just doesn't work. The problem is that you violated one of the essential but unspoken ground rules. So here are the ground rules that you must follow for success. Rule number 1. If either of the impedances are a complex impedance, then you must use a conjugate match with that impedance. If both are complex, then you get to choose which one of the two to use as your conjugate for the process. If neither of the impedances are complex, then conjugate matching is, well, kind of irrelevant, and direction of travel is equally irrelevant. Rule number 2. In the case of complex impedances, always move from the non-conjugate impedance toward the conjugate impedance. Direction does make a difference. Rule number 3. A viable solution only exists if the constant resistance and constant conductance circles cross on the Smith chart. We are traveling from one impedance to the other using the constant resistance and constant conductance circles as our path. If they don't touch, then we can't get there from here. Rule number 4. The longer the lines between the two impedances, the higher the Q and the narrower the bandwidth. The further away from the equator, the higher the Q and the narrower the bandwidth. Keep them short and keep them low for wider bandwidth. Rule number 5. The value we're interested in is always the destination value minus the start value. The signs will kill you. Rule number 6. The direction of travel on the constant resistance and constant conductance circles determines whether you are adding a capacitor or an inductor. So here's how it goes. If we're moving clockwise on a red constant resistance circle from our starting point, then we are adding a series inductor. If we are moving counterclockwise on a red constant resistance circle from our starting point, then we're adding a series capacitor. We do not move past the equator on the right when moving either direction on a red constant resistance circle. If we are moving counterclockwise on a blue constant conductance circle, then we are adding a parallel inductor. This is also known as a shunt inductor. If we are moving clockwise on a blue constant conductance circle, then we are adding a parallel capacitor. This is also known as a shunt capacitor. We do not move past the equator on the left when moving either direction on a blue constant conductance circle. Rule number 7. A choice of solutions may depend on whether you want your network to block some DC component of the source signal or not. Rule number 8, and this is an optional one. You can check your work by determining the input and output impedance of the circuit with the intended source and load impedances. They should show up as the complex conjugate of both, where either or both are complex. Now, on to our example. Well, before I start this exercise, I need to point out that I purposely chose impedances that would lay directly on the existing printed lines of the Smith chart. I did this to make it easier to demonstrate the principles. Your impedance can lay between the printed lines of the chart, and the same exact process would still apply. It would just be a little bit more difficult to accomplish because of the need for a good calibrated eyeball interpolation between the lines. Now, let's get into my example. I'm going to begin by getting our impedances ready for the exercise. In this example, we have a source impedance of 20 plus J10 and a load impedance of 70 plus J10. The first thing that we have to do is normalize each of these. This requires some sort of system impedance. Well, for impedance matching, the value that I choose for this, well, really doesn't matter because in the end, I'm going to be undoing this convention with the same number. Just for convention's sake, I'm going to use 50 ohms as a system impedance Z0. For a normalized source impedance, we would have 20 plus J10 divided by 50, which gives us 0.4 plus J0.2. And for the normalized load impedance, we have 70 plus J10 divided by 50, which gives us 1.4 plus J0.2. Both of our impedances are complex, so we have to use conjugate matching. So which one of these am I going to turn into a complex conjugate? For no other reason than it feels good to me to move from the source to the load, I'm going to choose the load impedance. The complex conjugate of the normalized load impedance is equal to 1.4 minus J0.2. Now we get to plot these on the Smith chart. So here is the mind-numbing full-color Smith chart. When we are plotting our impedances on this chart, the only lines we care about are the red ones. Let's start with the normalized source impedance, 0.4 plus J0.2. I first locate the 0.4 red constant resistance circle. Then I locate the 0.2 red constant reactance arc in the upper hemisphere because it is positive. I place a dot where these two meet. I'm going to call this point A. With our source impedance plotted, let's do the same thing with the normalized complex conjugate of the load impedance. I locate the 1.4 constant resistance circle and the minus J0.2 constant reactance arc. Where these meet, I place a dot. I am going to call this point C. With our two impedances plotted, we are ready to read the admittance values off of the chart. Well, we need to know the normalized admittance values of each of these to accomplish our goal. Now, there are two ways we could do this. We could do the complex math either manually or using Excel or using OCTAVE. Or we could just read them off of the Smith chart. I'm going to read the normalized source admittance values off of the Smith chart and avoid the complex math. To do this, I turn my attention to the blue lines. Let's look at the normalized source impedance dot first. I find the blue constant conductance circle that passes through my dot and note its value. I see here a conductance value of 2.0. Then I find the blue constant susceptance arc that passes through my dot and note its value. Remember, susceptance values above the equator are negative and below the equator are positive. I see here a susceptance value of minus J1.0. This is the part that we're going to be most interested in as we design our impedance matching network. So, the source's normalized admittance is equal to 2.0 minus J1.0. Now, let's go to the load's conjugate normalized impedance dot to do the same thing. I see the 0.7 constant conductance circle passes through my dot, so the conductance value is 0.7. I also see that the plus 0.1 constant susceptance arc also passes through my dot, so the susceptance is equal to plus 0.1. The load's normalized admittance is equal to 0.7 plus J0.1. We are ready to start looking at our map to see how we're going to be getting from point A to point C. Well, we always start at the impedance that is not the conjugate and work our way toward the impedance that is the conjugate. Going the other direction, well, it just doesn't work. So we're starting from the source dot at point A and looking for routes to the conjugate load dot at point C. Right off the bat, we can see 4 different ways that we could go from point A. We could travel up the blue constant conductance circle, which would be adding a parallel inductor. We could travel down the same blue constant conductance circle, which would be adding a parallel capacitor. The problem is that neither of these directions get us any closer to our goal. So what are our other options? Well, we can travel up the red constant resistance circle, which would be adding a series inductor, or we could also travel down the red constant resistance circle, which would be adding a series capacitor. Both of these seem to be getting us closer to our goal. In other words, moving toward the loads dot at point C. So let's follow these a little bit. We're looking for a place where the 0.4 red constant resistance circle will possibly cross the 0.7 blue constant conductance circle. I find 2 spots where this happens, one in the northern hemisphere and one in the southern hemisphere. This means that we have 2 viable solutions to our impedance matching circuit. So how do we choose between the 2? We ask ourselves 2 questions. First, do I want to block the DC component of my source signal from the load? If I do, then I choose the solution that sports a series capacitor. If I don't care either way, then I could choose either solution. Second, and hopefully the one that breaks the tie, is which path has the shorter travel distance? The shorter the travel distance, the wider the bandwidth. For the sake of our example, I just really don't care if I block the DC component of my source signal, so I'm going to look for the shortest route because I do want to maximize my bandwidth. I do a quick measurement with my ruler to discover that the northern route is most definitely shorter. I now place a dot at that spot, and I'm going to call this point B. Before we can determine the value for my components, we have to know the impedance and admittance values at point B. So we're going to read the normalized impedance and admittance values of our newly placed dot at point B right off the Smith chart. This is where we have to employ our calibrated eyeballs and carefully interpolate between the lines. I already know the resistance value because it lays right on my 0.4 constant resistance circle. The reactance seems to be just shy of the plus 0.65 constant reactance arc. I'm going to call it plus 0.64. Now for the admittance. Well, because this is where the 0.7 constant conductance circle crosses 0.4 constant resistance circle, I already know the conductance value is 0.7. The susceptance is going to be a bit more of a challenge. It is a little bit more than halfway between the minus 1.0 and the minus 1.2 constant susceptance arcs. My calibrated eyeball tells me that it should be about minus 1.12. Actually, I used a little bit of math on that one. Now, for the first part of our trip. So we're moving from point A to point B in the clockwise direction along a constant resistance circle. This means that we're adding a series inductor. I will call this X1. So what is its value? Well, the normalized reactance value of this inductor is found by subtracting the normalized reactance value at the start, which is point A, from the normalized reactance value at the destination, which is point B. This gives us 0.64 minus 0.2, which is equal to a plus 0.44. So we have an inductor whose normalized inductive reactance is 0.44 at the target frequency. But what is the inductor's actual value? The first step is to unnormalize it by multiplying its normalized value by the system impedance, which for this example, I used 50 ohms. This gives us 0.44 times 50, which gives me an inductive reactance in the real world of 22 ohms. If our target frequency is 50 megahertz, then our component value would be 22 divided by 2 times pi times 50 megahertz, which gives us a value of 70 nanohenries. Now, the next part of our journey, moving from point B to point C. Well, as we move from point B to point C, we are moving along a constant conductance circle. This means that we're going to be adding a parallel component. We must operate here with the susceptance values that we have been noting for points B and C. Because we're moving clockwise, we are going to be adding a parallel capacitor. I'm going to call this B2. The normalized susceptance of this parallel capacitor is found by subtracting the normalized susceptance of point B from the normalized susceptance at point C. That gives us 0.1 minus a negative 1.12, which is the same as 0.1 plus 1.12, which gives us a normalized susceptance of 1.22. But now we have to turn this into reactance using a simple division. Reactance is equal to minus 1 divided by susceptance. So we have minus 1 divided by 1.22, which gives us a normalized reactance of minus 0.82. We now have to unnormalize this by multiplying it by the 50 ohm system impedance. So that is minus 0.82 times 50, which gives us a capacitive reactance of minus 40.98 ohms in the real world. What does this work out to be at our target frequency at 50 megahertz? Well, the capacitance value is equal to 1 divided by 2 times pi times 50 megahertz times 40.98, which gives us a capacitor value of 77.7 picofarads. Well, you can check your work by calculating the input and output impedances either in the normalized world of the Smith chart or in the real world. This takes a bit of circuit analysis and some complex math. Here are my results. The input impedance is equal to JX1 plus this whole quantity, JX2 times the impedance of the load, divided by JX2 plus the impedance of the load. And with the numbers we previously arrived at, our input impedance comes out to be 20.077 minus J10.11 when the output is terminated with the load impedance of 70 plus J10. This is the complex conjugate of the source impedance of 20 plus J10. And that is exactly what it should be. Next is the output impedance. The output impedance is equal to, on the top we have JX2 times the quantity JX1 plus the source impedance divided by JX2 plus the quantity JX1 plus the source impedance. With the numbers previously arrived at, our output impedance is calculated to be 69.9 minus J9.55 when the input is terminated with the source impedance of 20 plus J10. This is the complex conjugate of the load impedance of 70 plus J10. Considering that this is arrived at using the Smith chart and our calibrated eyeballs, this is a check and a check. We have completed the first example showing how to design your own impedance matching circuit with an L-type A configuration. If you found this video helpful, please click on the like and subscribe. Thank you so much for watching. Until next time, Toodle-Oots.